My name is Stig Sørensen. I'm here with Sean Hansen, both working at Bloomberg. We're going to talk a bit about the evolution of telemetry at Bloomberg and where we, like, a bit of the path of where we started, where we are now, and so on. So, since we have two agenda items. The background, I'll do the background, and Sean will talk about the real technical stuff. First of all, what is Bloomberg? I'm quite surprised that everyone knows who we are. As Raj alluded to, we're started by the former mayor of New York. We're a Bloomberg professional service is our main product, which has 325,000 premium subscribers that rely on us for real-time market data, real-time news and analytics around the world. We both produce news and we produce media. We have more reporters than New York Times and some of these other more well-known media outlets. And Bloomberg Enterprise is getting bigger. That's really where we sell data at scale to whatever companies around the world that likes to look at data and interact with data. It's a reasonably large engineering effort. We're about 5,000 engineers, which is about a quarter of our company. In order for us to deliver this service, and why sort of monitoring becomes a bit interesting for us, we own and operate our own data centers, 2 main sites, 200 node sites around the world, plus the 325,000 customers run some part of our software on their workstations. With a company our size and our age, we have quite a diverse architecture that we need to monitor. We historically been very sort of in-house build. If we didn't build it ourselves, we didn't trust it. We're moving more and more to open source technologies, which sort of makes it interesting. And in addition to the Bloomberg professional service, we also deliver web, consumer web, professional web, and consumer and professional mobile applications. So the telemetry at Bloomberg. So what do we intend to do? We set out to deliver monitoring and alarming as a service for all of Bloomberg's infrastructure and application. So with the on-site service offering, with self-service, where engineers can think of us as an outside vendor, and hopefully don't have to use an outside vendor. So at this point, I'll hand over to Sean, and we'll sort of talk about how we actually did it.
All right, thanks, Stig. Is my mic on? Okay, here we go. I'm Sean. I'm one of the original developers of Bloomberg's latest monitoring system. I'll take you through sort of how we went about realizing our vision of what a monitoring system infrastructure should give. So you might notice this is not a fancy image. All of my images were taken from Reddit, and Legal pulled them from my slides. So I went through and drew everything, placed them with some Hansen originals for you guys. This one's a pie in the sky because when we were putting together our vision, it felt very far-reaching and far-fetched. And it's pizza because we're in New York. So I hope you like that one because none of them are any better than that. So as Stig mentioned, we own the physical layer, the data centers, and all of the software running on top of it. So we have a mix of systems publishing their own application stats. We have infrastructure publishing metrics for itself and on behalf of systems that use it, tens of thousands of systems. And like you said, we have an increasing number of open source products that can't natively integrate with us, and so we have some pull from that. So we have this big mix, so flexibility was pretty important to us when we were designing our system. So we have a lot of application owners out there, and they want alerts when their queue depth is full for 5 minutes or something like that. So we say, no problem. We've got infrastructure teams that want to alert other systems because they collected some metrics that say, hey, that system's probably in trouble. Okay. And then we got teams that say, hey, that infrastructure team's giving us tickets. They think we're in trouble, but we're not. We want to alert on our own criteria and exclude ourselves from those rules. So that's another bit for us. So at the end of the day, we have a system that needs to be low latency, high throughput, easy to use, flexible, and allows graphing and dashboarding capabilities. So that was no problem. So we have a lot a lot of monitoring systems at Bloomberg. Bloomberg's many decades old now, so we have basically every developer was responsible not only for creating their own product and deploying it, and they were also responsible for monitoring it. So there was a lot of afterthought on monitoring. It was mostly built as minimum viable products, and usually it was handed off to an intern to go ahead and say, yeah, build something that kind of makes sure everything's still not on fire. So this actually had a lot of issues company-wide. There was no global view of where any data lived. Multiple systems were collecting data, and a lot of it was overlapping and collected slightly differently. If you wanted to join any of this data together, you had to write a lot of glue code that was one-off, and you threw it away. And there was just a massive duplication of effort across the company, building and maintaining all these monitoring systems. And really, we just ended up with a bunch of differently shaped wheels, and some were square instead of round. But probably the biggest issue was that a lot of these technologies leaned on the things they were trying to monitor, because the software engineers that designed them were very comfortable with the thing that they had built. And they were like, oh, let me just leverage some of that technology as well. So how do we fix that? First, we had to basically completely set ourselves apart from all of the traditional in-house Bloomberg technology. That it wasn't really easy for us, because that's also what we knew pretty well. But there's some really good open source software out there, and with a bit of duplication of effort for what we already had at Bloomberg, we were able to do that. We also learned from our past mistakes. Baking a lot of logic into our clients meant it was really hard to change after the fact. Requiring people to redeploy, relink, recompile, all that stuff, it made it so realistically we could never ever deprecate anything. So in a new system, we basically made sure that any stuff we put in the client was as low level as we could make it and just got the data out as fast as possible. So we initially started by building our own StatsD agent. And what that did for us was it collected the system metrics automatically from all the different operating systems we've got, which we run a bunch of at Bloomberg. But it also supported StatsD, and we created BB-StatsD, which had tags, tag support, because we really needed tags. That was a big feature that we wanted to give. We later found a bunch of people were using open source products that were exporting data using InfluxStatsD, so we also kind of backported support for that into it. It also supported pre-aggregations in process. Some of our clients were very latency sensitive in their C++ tasks, so we built even forming the UDP packet in the StatsD protocol was just too high cost in the thread that they were calling from. So we built a very fast API that allowed them to do hundreds and hundreds of thousands of ticks a second and export just partial histograms or counters or whatever out to our agent for further aggregation. So we had some basic logic in the clients, a little bit more logic in the agent on the machine, but then most of our validation, transformation, persistence, rule processing, we did all of that centrally on a set of machines that were behind a Kafka wall that we put up. And like pretty much every monitoring system out there, something has to make sure the monitoring system's actually working. And we opted for just low-level external active health checks on the monitoring system to make sure it was baseline functional. And then we actually just published the metrics right back into the same system for any higher-level views or alerting. So this is actually a screenshot of our in-house monitoring tool for people to be able to set up their own rules. Because it's a shared system across the entire company, it's really important that users are able to go in, basically publish their intentions, register what namespaces or tags they want, and get their piece of the pie. So we have this UI, they can register namespaces, they can request an allotment of time series, and we'll basically alert them if they have published data that doesn't match what they've registered, or if they've gone past the number of time series we've allowed. And then they have to come to us to like sort of vet their use case, but we give them a fairly generous number of time series right off the bat to play with. It's also flexible enough that you can create rules like this, which is actually a firm-wide rule for all of the machines at Bloomberg. It alerts if your CPUs are basically running too hot. So some clusters do this basically all the time if they run nightly batch jobs or aftermarket hours jobs, or if like the developers are out there just running Bitcoin miners. So you can also see that there's exclusions in here. Developers can come in, say, my cluster is different, I want to know when it's even hotter than that, or I just don't want these alerts at all. And that's based on the cluster ownership, so they're able to go in and do it themselves, and they don't have to come to me, which is really good because they're probably happy they can turn off the tickets without waiting on me, and that gave me a lot more time to draw all these drawings for this presentation. So storing the data, scales wide became pretty much a joke to our team. We could solve pretty much every problem by just scaling wide. Cache coherency, variable naming, just scale it wide. We focused really heavily actually on storing all the data, and we didn't put very much thought on how we were going to pull the data back out. It was just like, yeah, it should have an API for that. So this was about 2014 when we were first proof of concepting this, and there was no real consensus on the best time series database. I don't think there is either now, but a lot of them were very immature back then. And we knew we were going to get to over 1 million data points a second just by pulling in all of the different legacy systems that we had. So we really focused on that. So we took a small number of products. We kind of proof of concept them on clusters, threw away a bunch just based on their architecture and design, kind of identifying bottlenecks that we didn't really want to deal with. And we chose a time series database that had some mildly high operational overload, very basic query features, but it was very fast ingest. So we released our product out there. We saw like kind of slow, steady growth over 2 years, and then occasional jumps in usage when a legacy system would start double ticking everything in. So after these 2 years, we're at 2.5 million data points per second, 200 million time series. Some metrics have high cardinality, like 500,000. So our initial solution did scale fairly well for us. It's on 10 times more machines than when we first released it. But every time we scaled up the number of machines, we scaled up the operational overhead for our team. More machine failures. It didn't always handle machine failures perfectly. And over time, we got new users, more data, more complex use cases requesting exceptional features that we didn't think about. So we started to project our 5-year growth, and we estimated we'd probably end up with 20 million data points a second and like 1 billion time series. We got to these numbers, we projected out just the baseline of what we saw for natural adoption, and then we added in the legacy systems that we knew hadn't migrated yet, and some use cases that were kind of presented to us, and we're at a scale that was large enough that we had to kind of say, all right, let's just take 10% of that data and hold off on the rest for later. So the first thing we tried was just taking our existing system, putting it on bigger, faster, more machines, and just throw the data at it and see what it could handle. It could handle all of the writes. We were able to push that to 20 million data points a second sustained, but we couldn't actually query anything out of it while it was doing that, and it still was really poor at handling high cardinality metrics, which was a pretty common use case. So while we could try to keep throwing more hardware at that, it wouldn't really solve that fundamental design issue. So we had to build something else. So we kind of revisited our requirements list, went back to square one, kept everything that we already had, but added more or kind of made some more specifications on things. It really surprised everyone on my team, I think. You can't just scale wide. You have to do stuff, and it really made everyone's life a little bit harder. Every piece of the system has to scale, and that means trying to identify bottlenecks sort of before you get to that point. And if you do it efficiently, you can actually just run fewer machines, which everyone's happy about because there's fewer hardware failures. We also added rollups in. Our previous solution, basically all data was just the raw data, any rollups had to be done manually, and it became really expensive, not just in disk utilization, but also historical queries pulled in a lot more data points than they really needed to. So this time around, we actually had some feedback, I'd say, from our users on our query API. So we were able to better understand their use cases. We wanted some caching layer so that repeated queries were handled efficiently. This became really useful for auto-refresh dashboards or rules that were being run that mostly had repetitive data time ranges, but with a little bit of new time on the end. We also had, probably one of our biggest requests was just providing some basic functions to allow derived metric calculations or manipulation. Configurable retention was a big one. In our previous solution, if it was per second data or per day data, it didn't really matter. It was all going to be stored for the exact same length of time. And we had some SREs out there that wanted the operating system metrics at 1 second granularity, and we had people publishing trend analysis that just cared about daily. So we really wanted to be able to say, all right, we can keep your data for 10 years, but your data we'll only keep for 3 days. And probably the metadata queries was our most important. Because it's a shared system, there's a lot of data in there that basically they don't know, nobody knows it was there except for the one person who published it. So if you can say, like, something happened on my machine at 12 o'clock and just sort of say, give me everything from that machine, let me drill down and try to find useful information that helps me analyze this issue, that's like a big win. So how did we actually get there? Our first thought was, like, maybe we could tack like Elasticsearch on outside of this thing and throw some other stuff out there, and we realized it's just gonna get really messy. Supporting metadata access is one thing, but configurable retention means running multiple clusters and doing request routing and all that stuff. And we were just like, at that point, we're starting to write a different time series database. We actually tried pretty hard to find an open source solution that got us like a good portion of the way there, that we could kind of submit pull requests and enhance, but it was hard for us to actually find something that would be enhanceable in a clean way and wouldn't just be like, oh, we'll take your thing and just rewrite it for you. So we actually just started going down the path of writing our own time series database, which is exactly what the world needed. So we took something like Facebook's Gorilla encoding, right? And we would have young and old data stores, the young data stores in memory, and the old data store would be on disk in something probably Bigtable-esque. Is any of this sounding familiar? So we got a great name. It was Time Vault. All of the pieces of the system had a Doctor Who themed name. The master ship was the Time Lord. It was actually, it was pretty solid, but really quickly we ran into a lot of the open questions that you'd expect. How do we handle failover, replication, query planning, math functions, flexible APIs? That's when I started to lose interest. So then I got this message from Stig. Hey, the Grafana folks mentioned something they built called Metric Tank. It's beta, they say it's reliable, we should check it out. So the name's good. I mean, it's not Time Vault, but it's still pretty good. This is what popped into my head. It's not a tank holding metrics, it's a tank just firing data points at people. Grafana Labs, you can absolutely use this as a logo. I know you're about to ask, take it. So how did it stack up? It was actually pretty well. It was one of the most impressive proof of concepts we actually used. It checked off almost everything on our list. And for high cardinality data, that was like the killer in our last system, it was 2 orders of magnitude faster. So that was pretty big for us. That opened up a lot of queries we weren't able to do before, especially things that involved firm-wide queries, being able to do analysis on, say, all of the parent clusters, comparing them this week to last week's CPU usage, things like that. We had to write Python scripts for our last thing that kind of went bit by bit and took hours to run, and now we could do it in a single query. The 2 spots that it didn't perfectly fit us were actually pretty important areas for us, though. Tags, very important to our system. I mean, that's why we had 2 different tag-based stats-D interfaces. And without them, you kind of deal with these long, awkward, sorted graphite paths. And it makes exploration really hard because the metadata queries are basically top down at that point with a lot of wildcards in the middle. Luckily, basically, as soon as I mentioned this to the metric tank folks, they were like, oh yeah, we're actually already working on that in Graphite, and we're gonna put it in metric tank, and they did. And I did chip in a little bit, add a couple of tag-based functions natively into metric tank, and we got a little green check mark for that. So with the tags that we got, we also got a lot of tag searching, autocomplete functionality, and that was basically everything we needed for the metadata queries we wanted. So we got another check mark. Sounds perfect. All green. Well, it's not perfect. We ran it at scale at Bloomberg, published all our data into it. There were a few spots where it used quite a bit of resources, and most of it was low-hanging fruit. We were able to just kind of remove some pointers or strings or whatever and contribute it back, and now it's running pretty smoothly. So we're not done with it. There's still a lot of things we want from it, and running a monitoring system at scale is pretty much an arms race with your users. As soon as you give them a feature, they love it, they forgot they never had it, and they want more. So we've got all sorts of things, query auditing and throttling to protect ourselves from these monsters that are using our system. Extrinsic tags to allow more flexible queries on data that we didn't actually publish. So if you have tags on your host, you don't have to publish all of those as labels with your thing. You can just say, that host also has these other attributes that we want to be able to search on later. And other things like, as Dieter mentioned, backfilling would be a good one, and possibly offline rollups for longer interval aggregations. If you want to do daily or weekly, you don't have to compute those rollups in memory. You can do them later as a background process. So sort of the recap slide here. Just because something scales in the one way that you looked at it doesn't mean it doesn't have bottlenecks somewhere else. We scaled well for writes, but we had the performance penalties for the mixed load, and high cardinality data specifically was just too slow. Metric tank, similarly, scales really well for writes, but it suffers the slowest member problem because every query has to broadcast out to a member of each shard group and then pull back the results. You have to wait for the slowest member of your cluster. You can sort of scale your throughput by adding more replicas, but you can't really scale latency the same way. So if you have very strict latency requirements, there's still some probably trickier problems to solve there. Finding metric tank was actually like a fluke, basically, I'd say. We wouldn't have found it in a Google search. We wouldn't have even known it existed if Stig wasn't talking to the Grafana Labs folks. And so keeping an ear to the ground, networking, and really just being open to evolving and changing your system is always gonna help you out. This one's just like a thing we noticed. One of the reasons this iteration of our metric system got to be so big and successful was it was really easy for people to use themselves. We didn't have to force any of the migrations over. We just kind of made a better system than they had, and people were able to opt into it. And my last piece is probably advice for myself in 2014, but I can't get it there, so I'll give it to you guys. Always abstract your integration points. We provided like a lot of layers around publishing data into the system, so we were able to spin up metric tank proof of concept in like a few hours, and in like a few days or a week, we were able to actually just double take all of our data into it. But on the other side, we've spent like 3 months trying to get all of our queries that are right now being made directly to our Timeseries database, our old one, kind of migrated over to metric tank because we didn't provide a similar abstraction for the query side. So everything's talking directly to the Timeseries database, and we had to write scripts to take in the JSON for our old series, kind of remunge it and put it back in with like this other like modified disclaimer, and it's been kind of a hassle. So now going forward, we've sort of ad hoc adopt the Graphite interface as our sort of pluggable. If we need to, we can actually sort of experiment with other storage engines just using the Graphite interface natively. All right, so thanks for listening. I don't know if there's time, but I can take some questions. I'll just take the first one.
Yeah, sure, you can take a few.
Yeah. So the first obvious one I'll handle before anyone asks it. I did not study fine art, actually. I was born being able to do that. So if that was the only question, maybe we're done. I don't know.